Performance analysis of QoS using WFQ in MPLS VPN environment with IPv4 and IPv6 for VoIP and HTTP applications. By AFAF Tarek Algold. Hadil Mofta Shiktor. Have you ever wondered why your online call might suddenly drop, or why a web page stops loading out of nowhere? In today's connected world, where we rely on the internet for everything from personal communication to business operations, smooth network performance is no longer a luxury, but a necessity. Unfortunately, we still face issues like delay and jitter, which have driven us to search for fundamental solutions. That is exactly what our project addresses today. Introduction. With the massive expansion in network usage and the increasing reliance on applications that require immediate and reliable connectivity, such as voice over IP, VoIP, it has become essential to move beyond traditional routing mechanisms. These networks, which operate on IPv4 and IPv6 protocols, primarily depend on a best effort model. This model treats all data packets identically without any differentiation or priority. This approach, despite its simplicity, is no longer sufficient to meet the strict quality requirements of modern applications. Problem statement: traditional IPv4, IPv6 networks use best effort, causing potential delays and packet loss for time-sensitive apps like VoIP. Project objectives: implemented QoS with WFQ to enhance performance. Measured impact on VoIP, delay-sensitive, and HTTP, speed, throughput. Compared performance across scenarios. Analyze and compare performance analysis with OpNet Modeler showed MPLS plus WFQ improves performance, lower delay, lower jitter, better HTTP. MPLS before MPLS, WAN protocols like ATM and Frame Relay faced major issues. They operated at layer 2, which doesn't align well with IP at layer 3, and scalability was a problem because adding branches required many virtual circuits, increasing routing complexity. MPLS addresses these issues by attaching labels to IP packets, allowing routers to forward traffic based on the label instead of the IP address. This label switching technique, similar to what ATM and Frame Relay used, changes the label at each hop rather than the destination address, improving efficiency and simplifying network management, which contributed to MPLS's popularity. How MPLS works. Labeling. When a packet enters the MPLS network, the ingress router assigns it a label. Instead of reading the full IP address at each hop, routers only read the label. Label switching. Along the path, routers do not reprocess the IP header, they simply swap the existing label with the next one. This makes forwarding faster and more efficient. Label switched path, LSP, a predefined end-to-end path is established. All packets with the same label follow the same route consistently. Label removal. At the egress router, the label is removed, revealing the original IP header. The packet is then delivered to its final destination as if it had traversed a standard IP network. MPLS VPN. MPLS with VPN allows multiple customer sites to connect securely over a shared service provider backbone instead of separate leased lines for each site. MPLS uses labels to forward packets along predetermined paths, keeping traffic for each VPN isolated and secure. This approach improves efficiency, scalability, and network performance, while allowing service providers to share network resources among multiple customers and simplify network management. IPv4 versus IPv6. IPv4. Address length, 32-bit. Configuration, manual or DHCP. Security, optional, IPsec. Not mandatory, broadcast, supported. NAT, commonly required. IPv6. Address length, 128-bit. Configuration, auto configuration, SLAAC, plus optional DHCPv6. Security, IPsec built-in. Broadcast, not supported, uses multicast and anycast. NAT, usually unnecessary. Quality of service, QoS, is a measure of a service's performance from the user's perspective. It's the ability to provide different priorities to different data or applications. Weighted fair queuing, WFQ. Weighted fair queuing, WFQ, is a scheduling algorithm used in network routers to manage packet traffic. It is an enhancement of the traditional fair queuing, FQ, algorithm, which aims to provide each data flow with an equal share of network bandwidth. WFQ adds a weight to each flow, allowing some to receive a larger share of the bandwidth than others, based on their priority. Key aspects of performance, measured by several factors, such as Packet loss, the percentage of data that doesn't arrive. Throughput, the amount of data successfully transferred. Delay, the time it takes for data to arrive. Jitter, the variation in the arrival time of data packets. Prioritization, QoS mechanisms are used to prioritize important data, like voice and video, to ensure they get the necessary resources. Importance, QoS is critical for applications that require high performance, such as voice over IP, VoIP, and real-time multimedia streaming. Description of the implementation of the technique. Project tools. This slide describes the implementation tools used in the project. Windows 11 is the operating system that provides the working environment. OpNet is a simulation software used to design, analyze, and evaluate network performance and applications. The case study. In this slide, we present the topology adopted in the project. The network was designed using OpNet to represent a realistic enterprise network environment. At the core routers, LSRs, are deployed to forward traffic efficiently. At the edges, edge routers, LERD, manage data ingress and egress to and from the network. Switches were added to connect local devices and to simulate actual workstations. Tested applications. This slide shows the tested applications in the project. VoIP, voice over IP, used to test real-time voice communication over the network. HTTP, Hypertext Transfer Protocol, used to test web traffic and data transfer performance. This slide presents the scenarios used in the project, IPv4 versus IPv6 networks comparison. MPLS VPN with IPv4 versus MPLS VPN with IPv6. MPLS VPN with IPv4, using WFQ, versus MPLS VPN with IPv6, using WFQ. The results. The image shows a comparison of voice jitter between IPv4, IPv6, and MPLS with WFQ over time. The results indicate that MPLS with WFQ provides better stability and lower jitter compared to basic connections. The image illustrates a comparison of voice packet delay variation across IPv4, IPv6, and MPLS with WFQ over time. The results show that MPLS with WFQ achieves lower delay variation, providing more consistent voice quality compared to basic IPv4, IPv6. The image shows a comparison of voice packet end-to-end delay between IPv4, IPv6, and MPLS with WFQ over time. The results indicate that the differences in delay are minimal, with all techniques maintaining nearly stable and close performance. The figure compares the HTTP object response time across different technologies: IPv4, IPv6, MPLS VPN, and MPLS with WFQ. The graph shows how the response time changes over the simulation period. It is observed that MPLS with WFQ provides the best performance with lower response time compared to the other protocols. The figure shows the HTTP page response time across different technologies: IPv4, IPv6, MPLS VPN, and MPLS with WFQ. The graph illustrates how page response time decreases over the simulation period. It is clear that MPLS with WFQ achieves the lowest response time, giving better performance than the other protocols. Conclusion: they reduced delay, jitter, and packet loss in VoIP, improving performance especially for MPLS applications with QoS. The improvement in HTTP was limited compared to VoIP. Important note: under low congestion network conditions, the improvements were not very significant, and no clear difference was observed between IPv4 and IPv6. The choice between them depends more on future scalability and addressing needs. Future work. Plan 1. Reduce bandwidth. Simulate higher congestion to test QoS under stress. Plan 2. Add more nodes. Increase network size and data volume to evaluate MPLS plus QoS in larger, busier networks. Thank you.